Ladies and gentlemen, hello and welcome, coming to you again, not quite live, from One Take Studios. Today's topic is measures of variation. By comparison, I've talked about measures of central tendency before, and those tell us about the center of our data. So variation, vary means change. So these measurements today show us how much differentiation, how much change, how much spread we have in our data. There's two of these measurements, well, I suppose technically there's three of these measurements, but two are probably going to focus on the most here. The easiest one is range. You've heard of range before, most likely. Range is the difference between the largest and smallest values. So if I have a set of data, and the smallest number is 2, and the largest number is 20, careful. In English, we would say, well, my measurements range from 2 to 20. Which is delightful. However, that does not work for statistics. You would actually need to take the difference here. Difference in this case literally refers to subtraction. And so if I'm doing 20 minus 2, I would say that my range is 18. All right? So for this, note to self, you want to have one number. If you are answering a range question with more than one number, you have a problem. All right, so one number, do the actual subtraction, and that's going to be your range, largest minus smallest. All right, second is actually the big hitter for the day, and this is going to be variance and standard deviation. I'm lumping them together because they are most definitely tied together. I'm going to focus largely on standard deviation. Variance is just a small jump from that. Oh, goodness gracious. Populations versus samples. We have two slightly different formulas for standard deviation based on whether or not we are working with a population or a sample. So I'm actually starting with the population, and this is the formula. I would like you to know what the pieces parts of this for the formula are. This is sigma. This is a Greek letter. This is lowercase sigma. We are talking about population, so Greek letters often used to represent population measurements. So this is a population. We are looking for the sum of x minus mu. Well, mu, if you remember, mu is the mean. Yes, mu is the mean, again, of a population. So this is a population variable. This is a population variable, both in Greek. And we are dividing by n. And n is the number of values that we have. I would like you to understand the concept behind this. So I'm going to give you an explanation that is not a technical definition. It is not a technical definition, but it will really help you understand what's happening. We are saying I have a whole bunch of x values, all right? So I have a data set, a whole bunch of x's. And that set of data values has a mean, or an average if your brain likes that better, but really try to use the word mean. This is saying I'm going to take every single data value that I have, and I'm going to subtract it from the mean. Subtraction often gets us distance. We talked about range. Subtraction tells us how far they are apart. So this is distance. So I'm taking my first value and finding out how far it is from the mean, the middle of the data. My second value, minus the mean, so how far this is from the mean. I am looking for the distances from all of my data values to the mean for that set. Some of my distances could be negative, because what if my number is below the mean? So if we square, we can get positive distances. Again, this is not a technical definition, but this is just to kind of help your brain work with some stuff here. What we're going to do is then we're going to add all those distances together. So the squaring makes some positive numbers so that we don't have things canceling each other out. I'm adding a bunch of distances. I'm adding a bunch of distances and dividing by how many numbers I have. Please tell me that that sounds like a mean to you. That's what standard deviation is, kind of, sort of, so that your brain can put everything together. We are talking about the average distance of our numbers from the mean, the average distance, how far these are from the center of the data. That means that if this value is something that is large, we're talking numbers that are spread out a lot from the mean. If this number is small, we're talking numbers that are very, very close to the mean. That is your nutshell. Again, that is not a technical definition. If you're looking for why is there a square root, well, my brain kind of says, well, I squared it, so I should take the square root to undo that. Is that technical? No, it is not. And if your brain says this is an average, you want to be careful with this because this is not the same as simply adding up and dividing how many numbers you have. This is more complicated than that. What is the difference between a population and a sample? Well, check this out. You're going to see a ton of similarity here. It's a sample. So notice we're not using Greek anymore. This is the lowercase s. And instead of using mu, which was the symbol for mean for a population, we're using x bar, which is the symbol for mean for a sample. So structure's the same, change of variables to indicate population versus sample. The only real change is this n minus 1 thing here. And this is interesting because this is saying however many numbers I have, I want to actually divide by something smaller. When you divide by a smaller number, you get a bigger one. Why would I want this number to be bigger than this one? This is saying this is a sample. I do not have all of my data values. So I am willing to admit that I might have some extreme values that didn't make it into my sample. And if I have some extreme values, that means that my data would be farther spread out. Hence, I would like to have a larger standard deviation to compensate for that. So again, dividing by a slightly larger, so however many numbers I have, this is going to be one less. Dividing by something smaller makes this bigger overall to compensate for the fact that it's a sample, to compensate for the fact that there might be values out there that we're just not aware of. And since we don't know them, we're going to make the standard deviation a little bit wider just in case. All right, so that's our comparison there. Hold on to those. I'd like to run an example so we can see what this looks like. So what I have for you here is a very small set of numbers, because small is easy for us to deal with. My set of numbers is 1, 2, 3, 4, 5, because that makes me happy. 1, 2, 3, 4, 5, which has a perfect balancing point or mean of 3. So I am saying that the mean is 3. Notice what I've said for you already without using the word. Because of the variable I chose, I have told you that this is a population of numbers. So u minus 3. So u minus 3, u equals 3. Holy crud. This is why this is 1 takes studios. Mu equals 3. This is our mean. And so if we go back to this formula right here, this is what's happening. We are saying, I'm going to add a bunch of things together, and so you can see the addition taking place because we're adding. I'm taking every x value. So my x values were 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. And I'm subtracting them from the mean, just like it says. So the first x value minus the mean, the second x value minus the mean. So if the mean is 3, 1 minus 3, boom, 2 minus 3, 3 minus 3, 4 minus 3, 5 minus 3. We are squaring those values, dividing by how many numbers we have. We have 5 numbers in our set, and that is going to give us our standard deviation, which in this case happens to come together quite nicely because this ends up being, I'm going to slide this in, so sigma is equal to the square root of 10 over 5, which is the square root of 2, which is approximately 1.41. So this would be the standard deviation for this population of values. Some places, depending on where you go to college, there are professors that make you do this by hand every single time. I like understanding it. I think it's important that you understand it. I don't think it's important that you be able to punch numbers for all of eternity. So I'm going to show you something else here in a moment, as soon as I come back to variance. I told you that it's very closely linked to standard deviation, and it is. It is simply the standard deviation squared. So, if standard deviation is sigma, the variance would be sigma squared. Or, if my standard deviation is s, my variance would be s squared. Whatever I had before I took the square root, that number is the variance. So the variance is simply the standard deviation squared. So if I go back to this for a moment, and I said I wanted to know the variance, because this again is standard deviation. I'm using SD for standard deviation on this. Get the focus, there we go. What would sigma squared be? Well, what did I have before I took the square root? 2. So this has a variance of 2. Take the square root, there's my standard deviation. Okay? Very closely related to each other. Switching screens for a moment here, I want to go to this guy. Nope, not that one. That's kind of silly. I want to go to this one. There we go. Alright, so I have opened up a new document and I would like to go to lists and spreadsheets because I would like to be able to tell the calculator what lovely numbers I have. And I have a 1 in my data set, and I have a 2, and a 3, and a 4, and a 5. Make sure you hit enter that last time, otherwise, or down arrow something, because you don't want your highlighted box stuck on that 5. We are going to find everything fun and exciting. The same place we find everything fun and exciting is the menu. We are actually working with some statistics right now, and we would like to do some calculations, and we have one variable. We have a list of x's. We do not have ordered pairs. So let's go to our one variable stats. Yes, we do have one list. Yes, it is in column A. That is the first column on my spreadsheet. Great. And we have a whole bunch of stuff. Look at that. X bar is 3. The mean is 3. Wait a minute, how come x bar is 3? I thought that mu was 3. Well, calculating x bar and calculating mu works the exact same way. So the calculator puts together the value for you and says, I'm going to call it x bar. And if you want to call it mu, well then you should call it mu. So you have to know if you are looking at a population or a sample. The calculator at this point is going to just use the notation for a sample. All kinds of crazy stuff, bits and pieces of formulas. Hey, look at that. Look at that. That's an S. That's a sigma. S, sigma. Ooh, 1.41. Isn't that what we just got? Hey guys, if we run one variable stats on our list of numbers, one of the things that it'll crank out for us is the standard deviation. And in fact, it's being so cautious, it's saying, you know what, I'm going to help you out here because I don't know if 1, 2, 3, 4, 5 is a population or if it's a sample. So I'm going to run both numbers for you, and it ran it as a population, so here's sigma, of 1.41. But it also ran it as a sample, just to be on the safe side, as 1.58. And if you remember what I said, the only difference really between these formulas is that here we are dividing by a slightly smaller number. When divide by a smaller number, it creates a larger number. So again, for this data, if this was a sample and not a population, we're saying we'd like to compensate for the fact that there could be unknown extreme values. So we're going to say that the data is spread out a little bit more than we would if we knew it was a population and we knew all the values for sure. That's it, guys. That's what I got for you for today. All right, so be careful with your variables. Pay attention to whether you have a sample or a population. And hey, don't forget range. What's your answer for range? One number, right? Good, good, good. One number only. All right. Thanks, guys.